Hello everyone, welcome to this Thames Valley Learning Partnership event with Dr Stephen Lynch, and we're very excited to have him here with us today. So before I pass over to Stephen, just very quickly, I'd like to say thank you to St Joseph's Catholic High School for hosting this event, and also to Speakers for Schools for putting us into contact with Stephen. Great, that's all from me. If I can pass over to you now, Stephen, thank you.
Okay, thank you very much, Claire and Emily, for organising this talk. So I'm now going to share my screen with you, and you can just tell me whether you can see this or not.
Yes, we can see that.
Fantastic. Okay, so as I say, my name's Stephen. I'm a university lecturer at Manchester Metropolitan University. I'm also the chair of the Northwest branch of the IMA. I am a STEM ambassador and I am a speaker for schools. So I've been going into schools now for about 30 years, giving this kind of talk. So the title of the talk is Brain-Inspired Computing. And luckily for me, the invention can be explained just by this one simple picture. Yeah, so this one simple picture depicts our invention. So today I'm going to show you that maths has a broad range of applications in the real world. I'm also going to demonstrate that you need programming to solve the majority of real world problems. So that the maths that you learn at school isn't really enough to tackle real world problems. I'm going to reveal that mathematics is a much loved subject, and believe it or not, it can be fun to study. And hopefully at the end of this presentation, we hope you will be inspired to think about studying for a degree in mathematics at university level. Okay, now I'm not sure how many of you have heard of a package called Python. Python is the most popular programming language in the world at the moment, and we can use Python to solve our maths problems. There are other maths packages, for example, Mathematica, MATLAB, and Maple, and these packages are used predominantly in most universities around the world. If any of you are thinking of doing an engineering degree, then nearly every engineering department in the world will use MATLAB. So I've written books on all of these packages, and you'll notice that I've been able to depict our invention on the front of my books. Okay, so as I said, mathematics is loved by our students. So at Manchester Metropolitan University, we have over, I think it's 36,000 students at MMU. So that's for Manchester Metropolitan University. And each year the Students' Union run a competition, and the students vote for their favourite course. And as you can see, mathematics has been shortlisted on 8 occasions over the last 10 years. And mathematics has been voted course of the year in 2020, 2018, and 2012 by our students. So students who go to university to do mathematics really enjoy the subject, and hopefully by the end of this talk you'll understand why. In 2018, the UK government published 2 reports. The first one was this computational modelling technological futures. This is known as the Blackett Review, and it highlights the importance of mathematics and computational modelling to the UK economy. So on Google, if you just type in computational modelling, technological futures, the Blackett Review, you can read that report for free on the internet. Shortly afterwards, in April 2018, Philip Bond produced this report. So it was an independent report about knowledge exchange in mathematics. And amongst the many recommendations in this report was the recommendation that all math students should acquire a working knowledge of at least one programming language. Now, currently, that doesn't really happen across the UK. Okay, so mathematicians generally aren't introduced to a programming language on their degree, but that situation is changing. Okay, so as I say, today we're going to talk about brain-inspired computing. So I'm going to talk to you about neurons and the brain. Our first application is in computing. So we'll be talking about computing with something called a threshold oscillator. I'll explain what that is in a few moments. And you can see there are potentially 5 avenues of research. So we can use threshold oscillators using superconducting devices, or the threshold oscillators could be biological neurons, or the threshold oscillators could be transistor-based oscillators, The threshold oscillators could be all optical oscillators. And finally, we've got this new device called a memristor. Okay, and again, as we go through the talk, I'll explain what most of these terms mean. So from this one simple idea in mathematics, you'll see already we've got 5 potentially big avenues of research. What are the possible applications of this? We believe with this invention, we can build the world's fastest supercomputer. The picture on the right here is a photograph of the world's fastest transistor-based supercomputer. And this was made by Japan. That's the first avenue of research, to build a new type of computer. And the second avenue of research is in medicine. So we want to build what we call an assay or a test circuit for neuronal degradation. And this means that we will build circuitry out of biological neurons. Now, some of you may have heard of artificial intelligence. It's been on the news. It's a new branch of science, relatively new branch of science. So artificial intelligence is about machine learning and what we call deep learning. And there have been some very exciting developments in recent years. And this is where we're getting computers to act like the human brain. So we can program computers to act like the human brain. That's called artificial intelligence. Now, our invention called brain-inspired computing is kind of the opposite. So what we do is we take how the brain works and we're going to build a conventional computer. And we call this binary oscillator computing. So this is using biological brain dynamics to create a powerful conventional supercomputer. So these two are opposites. Artificial intelligence and brain-inspired computers are kind of poles apart. Okay, so what we talk about these neurons? So the average human brain has got about 100 billion neurons, 100,000 million neurons or cells. The slide here, so these sections here are slices of a mouse brain, very small sections of a mouse brain. If we put these images under a scanning electron microscope, then we get images such as this one here. So this is one slice, very small area of a mouse brain. Then we can use our packages, Python, Maple, MATLAB, or Mathematica, and we can use something called image processing, and we can reconstruct a 3-dimensional image of the neurons in a mouse brain. And then we can also use image processing techniques to give colors to the individual neurons. So all of these colored cells here, these are all neurons. So that you'll see there's a cell body, like the blob. And then these branches coming out of the blobs, these are called axons. And the axons are how the neurons communicate with one another. So these are pictures of actual mouse neurons reconstructed using image processing techniques. What we can do then is we can see how these neurons are connected together in a small section of mouse brain. So this picture here represents a very tiny cube of synaptic connections between neurons in a mouse brain. Now, the idea behind this research is we wanted to build kind of a model like this for one human brain. So imagine, we want to see how are all the neurons in one human brain connected together. Now, you'll see here that using current technology, it would take 4 million years to produce a map like this just for one human brain. So hopefully that will give you a good idea of how complex our human brains are. So as I say, you've got 100 billion neurons, and there are thousands of trillions of connections between these neurons. It's definitely, it's the most powerful computer known to the human race. Okay, so I'm going to talk about oscillators. So what do we mean by these oscillators? So the oscillator you are probably most familiar with is circadian oscillations. So these are oscillations of our wake-sleep cycle. So in the morning, we wake up, and then we do things in the day, and then at night time, our brains shut down again, and we go to sleep. So every 12 hours, we go into this wake-sleep cycle. So that's called a circadian oscillation. The human heart, within our bodies, our human heart, ba-bum, 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 that is an oscillator. To see the oscillations, if you go to hospital and get connected to a heart monitor, then you can actually see the oscillations on the heart monitor. And you'll notice that the average human heart beats about once every second. Boom, 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 boom. Okay, now cells in our brain, so neurons in our brain, are also oscillators. But these oscillators oscillate 1,000 times in 1 second. So you're currently thinking now, and billions of your oscillators in your brain are all oscillating really, really quickly, 1,000 times in 1 second, which is hard to get your head around. You know, try and do 1,000 beats in 1 second. That's how fast your neurons are oscillating. The picture on the right here is a process called angiogenesis. Again, this is from biology, and this is to do with how new blood vessels form. And as you can see from the graphs here, the processes in angiogenesis are also oscillatory. Retinal cells in our eyes oscillate, muscle cells oscillate. Our human bodies are just full of oscillators. Okay, so where does the mathematics come into this? Well, in 1952, Hodgkin and Huxley were trying to figure out how do these neurons communicate with each other. So they looked at a giant squid axon. So the picture on the right here is a giant squid. And when the giant squid thinks, it sends messages to this motor neuron, and a motor neuron will tell the fin to go up or down. Yeah, so we have voltages and electric currents flowing down this giant squid axon. And Hodgkin and Huxley were able to simulate this process using simple electrical circuits. And these electrical circuits consisted of resistors, inductors, and capacitors. And once they built the circuits with resistors, inductors, and capacitors, they were able to write down the mathematical equations to model these action potentials flowing down these axons. They did the research at University of Plymouth, and you can actually visit their lab. And once they finished with these giant squid axons, which are about 1 meter in length, they threw them up to the ceiling, and you can actually go to the lab and you can still see these axons suspended from the ceilings at the University of Plymouth. For this work, they were awarded the Nobel Prize. Okay, now this picture is depicting what we call excitatory neurons, which I've colored here green, and inhibitory neurons, which I've colored red. Now, obviously in the brain, your neurons are not green and red. Yeah, this is just for schematic. We've also got a postsynaptic neuron, which I've colored blue. So what happens is we give a little bit of electric current to this excitatory neuron, and we make it start oscillating. Okay, so this one starts to oscillate. So electrical signals go down here, and then we have the electrical signals get converted to chemical signals. Those chemicals then diffuse across a gap, and they go to the postsynaptic neuron and get converted back to electrical signals again. So straight away with these neurons, you'll see we've got biology, physics, and chemistry. All of these STEM subjects in just figuring out how neurons work. Now, if we switch this excitatory on, so it starts to oscillate, as in here, then it sends chemical signals to the postsynaptic neuron, and it makes the voltage in the postsynaptic neuron rise. And when the voltage reaches what we call a threshold, the postsynaptic neuron will also start to oscillate. So if you can see my picture here, we have the excitatory neuron switches the blue neuron on, and we call that excitation. Okay, similarly, we have these red neurons. So these are called inhibitory neurons. Now, when we excite an inhibitory neuron, it sends inhibitory neurotransmitters to the postsynaptic neuron, and it actually causes the voltage in the postsynaptic neuron to drop, and it moves the voltage away from the threshold. So the way to think about an inhibitory neuron is an inhibitory neuron will switch an adjoining neuron off. So this neuron is set to inhibit this neuron. It switches it off. So we have excitation and inhibition, and that's what's going on in our brains all the time. So when you wake up in the morning, lots of excitatory neurons start firing to wake you up. And at night, when you're trying to go to sleep, your inhibitory neurons should start firing to calm your brain down and switch a lot of neurons off.
Stephen, we have
Yes.
a quick question that's popped up. It says, would you recommend the R statistical language as a useful tool for data analysis at school and beyond? So I don't know if you want to answer that. And then obviously if any of the other students or staff watching this event and this talk, if you want to include any questions again in the Q&A box as Stephen's talking, please do feel free.
Yeah, so I will talk about packages later on, but R is a specialist statistics package, and yes, it is fantastic for data science. But you can also use Python. So we teach our students Python, MATLAB, and R. So yeah, R is the best package for data science. But I'll say more about programming a bit later on. Okay, now the picture on the left here was generated with Python, or you could use MATLAB, Maple, or Mathematica. So the lower graph shows input current. So this curve here is showing electricity in milliamps. Okay, so there's only milliamps going on in the brain, and the time is in milliseconds because all of this is happening 1,000 times in a second. So you can see here when the input current is low, the voltage just remains constant to say minus 70 millivolts. So in our brains, the voltage of the neurons in our brain is about minus 70 millivolts. If the current is quite low, you'll see that the neuron doesn't oscillate. It just stays at what we call resting potential. And then as the current into the neuron rises, you'll see we get to this point where there's a single spike, but then we go back to resting potential. And then we get to about 7 milliamps where the neuron starts to oscillate. So you can think of we're pumping current into the neuron, and as soon as the current reaches a certain value, the neuron starts to oscillate. So that's called a threshold oscillator. Now, again, using packages such as Python, Maple, MATLAB, and Mathematica, we can also simulate excitation. So this picture here shows the green oscillating neuron switches the blue neuron on. So this is depicting excitation. And the picture on the right, we have the red oscillating neuron is inhibiting the blue neuron. So we have excitation and inhibition. Yeah, that's what goes on in the brain. So you'll see again straight away we're talking about electric currents and voltages, and all of these science topics are important in order to understand how the human brain works. And obviously there's lots of biology in there as well, and obviously mathematics, and there's going to be computing. So the mathematical modeling of neurons really began in 1952 with Hodgkin and Huxley. And as I say, they won the Nobel Prize for their work. Now, using the Hodgkin-Huxley models, if we wanted to simulate one human brain, we would need a very, very powerful computer, which currently the world does not have. We do not have a computer powerful enough to simulate how 100 billion of these equations could connect with 1,000 other. We just don't have a computer powerful enough. So now I'm going to show you the power of mathematics. Why is mathematics such a useful subject? Well, you'll notice that over the decades, what's happened is mathematicians have simplified the equations. And in 2005, Izhikevich came up with biophysically meaningless mathematical models, but they were much, much simpler than the Hodgkin-Huxley model. Okay, so here we have the presynaptic neuron and a postsynaptic neuron, and you'll notice here there's a synaptic gap. Okay, so this synaptic gap, so we have electric current, it bursts these bubbles, we have chemicals go across the synaptic gap onto these receptors, and then they get converted back to electrical signals again. So if electrical signals get converted to chemical signals, back to electrical signals. You can see it's all very, very complex system. Okay, so in 2005, as I say, Izhikevich devised a much simpler system. And using his system, he was able to connect 100 billion of these equations together using 1,000 trillion connections. And he ran this simulation for 30 days and 30 nights. Now, the little red dots here represent excitatory neurons, and the little black dots represent inhibitory neurons. And this picture is just showing 50 million, so only 3% of the neurons in this brain. Okay, and if you look at the time scale down here, down below, you'll see that the computer ran for 30 days and 30 nights, and it simulated 1 second of brain activity. So what you're seeing here is kind of a slow motion, depiction of how the excitatory and inhibitory neurons interact. Again, if you're interested in this research, this is called the Blue Brain Project. So that this is ongoing research. Now, rather aptly, today is the 73rd anniversary of the baby computer. Okay, so what's this baby computer? Well, in 1948, Manchester University built the world's first programmable computer. And if ever you visit Manchester, if you go to the Museum of Science and Industry in Manchester, in 1998, volunteers built a working replica of the baby computer, which you can see here, the picture on the left. So this is a replica of the world's first programmable computer. And as I say, if you look on Twitter and other resources, you'll see a lot of people have posted today is the 73rd anniversary of the baby computer. So we're very proud of that in Manchester. The picture on the right here, this is something called a vacuum tube oscillator. Yeah, vacuum tube oscillator. And you can just about see in this computer here, there are lots and lots of these oscillators. So this was a principal component in the world's first computer. Okay, a vacuum tube oscillator. Now, these devices are quite large and they consume a lot of power. Yeah, they consume a lot of power. So in the 1950s, the transistor was invented. Now, the transistor can be built a lot smaller than this vacuum tube oscillator. And the way to think about a transistor is like a switch. It's like an on-off switch. And because the transistors used a lot less power than these vacuum tube oscillators, that's why all computers started to be built with transistors instead of vacuum tube oscillators. And that's why now your mobile phones, your games consoles, your computers, everything is built with transistor circuitry. And these transistors can be built on very, very small scales. So for example, on a circuit the size of a stamp, you can fit 1 billion of these transistors. Okay, now modern computers compute with something called binary. So a binary number is either a 0 or a 1. So we only have 2 digits in binary, a 0 and a 1. Now the human race, we've evolved using the denary number system. And we've probably evolved with a denary number system because we have 10 digits on our hands, 10 digits. So that's why we are comfortable working with numbers base 10. Now, if we wanted to represent the number 9, the denary number 9 with binary, then we would need a 1, 2 to the power 0. 2 to the power 0 is 1. We would need no 2s. 2 is 2 to the power 1. We'd need no 4s. 4 is 2 to the power 2. 2 squared, and then we need an 8. 8 is 2 times 2 times 2, or 2 cubed. So in binary, this is like your units, your tens, your hundreds, and your thousands. So in binary, the denary number 9 is represented by the binary number 1, which is 1,000, no hundreds, no tens, and a unit. So the binary number 1001 represents the denary number 9. Now, with the first computers, we represented this with light bulbs. Light bulb on, light bulb off, light bulb off, light bulb on. This would represent the number 9. Yeah. Either with binary, it's like 1001, or you can think of this as a denary number, a 1001 is equivalent to a denary number 9. Now, just like with arithmetic you do in primary school, you can also add binary numbers together using exactly the same rules that you did in primary. Okay, so I haven't got time to go through this, but again, if you're interested in binary, There's lots of resources on the web, and you may even cover some binary in school. Now, this is our invention. So we've called this the binary oscillator half adder. You'll see it's a very simple design. We have two threshold oscillators. We label these oscillator 01 and oscillator 02. We have 4 input connections. I've colored these green because these are all excitatory. So these are all excitatory connections. And we will have 1 inhibitory connection, which I've colored red. So the greens are excitatory connections and the red is a inhibitory connection. Now, rather oddly, you'll see that the ratio of excitatory connections to inhibitory connections is exactly 80% to 20%. And remember what I said at the beginning is 80% of the neurons in our brain are excitatory and 20% are inhibitory. So we set oscillator 01 to have a low threshold, which means we don't need to pump much, we don't need much current going into oscillator 01 and it will start to fire. Oscillator 02 has a higher threshold, which means you need a higher threshold in order to switch on oscillator 2. So oscillator 1 has got a low threshold, oscillator 2 has got a high threshold. Okay, now as I say, modern computers and telephone, your phones and your computer consoles are built with transistors. So Ben Eater has got a really good set of videos on YouTube, and he shows how you can use transistors to make logic gates. So the circuit here on the right is what we call a breadboard circuit. So we have these two black shapes here. These are transistors, and you can see there's lots of wires connecting this circuitry together. These little things here are switches, and then we have an LED bulb. Okay, now this is called an AND gate. Okay, so this is called an AND gate. And this light bulb will only light up if we push this button and this button at the same time. So if you look at this truth table here, the output, so this bulb will only shine when we push both buttons. Okay, so A has got to be 1 and B has got to be 1 in order to get the output to be a 1. So if neither button is pushed, this light bulb stays off. If only B is pushed, the light bulb stays off. If A is pushed but not B, the light bulb stays off. And as I say, the only way you get the light bulb to light is if you push both buttons at the same time. So in school, in a secondary school, you can build these circuits. They are very, very simple circuits to build. And pictorially, we can show on pen and paper, this is your LED. So this, these little arrows show that the light bulb shines. And here are our 2 transistors. So this forms a loop. And as long as these are both pushed down at the same time, then current will flow and the light bulb will light. So we call that an AND gate. Okay. The next gate we're going to look at is called an exclusive OR gate. Okay. Now you can see that the circuitry for this logic gate is a lot more complicated. In this case, we need 5 transistors. So again, these little devices here are all called transistors. Again, we only have 2 switches. We only have 2 inputs, A and B. And you'll see this is the symbol for an XOR gate. So with an exclusive OR gate, we have that the output is 1. So the light bulb will shine if either A or B is on. If A and B are both off, then the light bulb is off. If A and B are both on, then light bulb is off. So as I say, the light bulb will only light if either A is on and B is off, or B is on and A is off. Okay, so that's called an exclusive OR gate. Now you're probably wondering, why would we need an AND gate and an exclusive OR gate? Well, this gives us something called a binary half adder. Now, in order for your phones to work and computers to work and your games consoles to work, you need these components to perform what we call logic. And the most basic logic component of any computer is called a half adder. And we use the half adder to add 2 bits together. So we're doing 0 plus 0, 0 plus 1, 1 plus 0, and 1 plus 1. It all sounds very simple. So this is the circuitry we need with transistors to make a logic circuit for a binary half adder. And here is the truth table. So this is the truth table. So if A and B are both off, then the XOR gate gives us what we call the sum, and the AND gate gives us the carry. So the easy way to think about this is the carry is your tens, and the sum is the units. So we're just adding bits together. 0 plus 0, 0 plus 1, 1 plus 0, and 1 plus 1. So if you look down the first column, if A and B are both 0, then the sum is 0 and the carry is 0. So we simply say 0 plus 0 is no units and no tens. If you look down the second column, so now suppose we push button B, then we have 0 plus 1. The sum comes on, but the carry stays off. So what we have is 0 plus 1 in binary is 1 unit and no tens. And then if we push A and leave B off, then we have 1 plus 0 is again 1 unit and no tens. And then if you push A and B at the same time, then the circuitry here with the transistors, so if we push A and B at the same time, then we'd need 2 LEDs, and what we get is the sum is off, that's your units, but the carry goes on. So in binary, that's 1, 0. So in binary, 1 plus 1 is 1, 0. It's like a 2 and no ones. Yeah. So 1 plus 1 in binary is 1, 0. So using transistors, we need an AND gate and an XOR gate. For the AND gate, remember we need 2 transistors. And for the exclusive OR gate, we need 5 transistors. So already you can see here we've got 7 transistors and the circuitry is quite complex. Now, this is our invention. So this is the brand new thing that we came up with in 2008. So again, it's called a half adder. Now, instead of using zeros and ones, so transistors are switches, on, off, on, off. With threshold oscillators, an on or a 1 is an oscillation. So if an oscillator is oscillating, that's what we think of as a 1. And if the oscillator is not oscillating, that is our 0. Okay, so if A and B are both off, if we look down the first column, A and B are both off, then the sum stays off and the carry stays off. There's not enough current going into the oscillators, so they both stay off. Now, if either A or B are on, so if we look at the second and third columns here, if either A or B is on, then we have sufficient current goes into oscillator 1. So we have a bit of current goes into oscillator 1, that one switches on. Yeah, so oscillator 1 switches on. And if we look at oscillator 2, only A or B is on, so we don't have enough current to switch on oscillator 2. That one stays off. So if we look down the columns 2 and 3, then we have 0 plus 1 is the sum is on, but the carry is off. And 1 plus 0 is the sum is on, but the carry is off. So 0 plus 1 is 1 unit and no tens, and 1 plus 0 is 1 unit and no tens. Okay, now hopefully everyone is with me so far. The next bit is the most complicated bit, and this is how we got our invention. And nobody else in the world had thought about this, and you'll see it's really, really simple. Okay, but nobody's thought about it. How do we know nobody's thought of this before? Because we filed for a patent and we were granted the patent. Okay, so this is our really simple idea. So now, what if A and B are both on? So we push both buttons, A and B. Okay, so here's our A and our B are both on. Then we have lots of current goes into oscillator 1. Lots of current goes into oscillator 1. That starts to oscillate. Okay, now because A and B are both on, lots of current also goes into oscillators 2. That one starts to oscillate as well. But then we have an inhibitory connection from oscillator 2 to oscillator 1. So oscillator 2 stops oscillator 1 from firing. Oscillator 2 inhibits oscillator 1. Yeah. So looking down the column, we have 1 plus 1 is no units and a 10. And believe it or not, that is our invention. Yeah, that is the invention. That's how easy it is. That's how simple the invention is. I've been into primary schools, and I've explained this idea to primary school children, and they understood the idea. So you can see it's a very, very simple idea. And as I said, this is the basic component we need in order to add 2 bits together in computers. And this is what we call logic. So these are the logic operations in computers. Now, why is everyone getting excited? Okay, now if we use transistors to add 2 bits together, remember we need an XOR gate with 5 transistors, and we need an AND gate with 2 transistors. So altogether, we need 7 transistors to make a half adder with, with transistors. Now, the next most complex logic circuit is what we call a full adder. And we use a full adder to add 3 bits together, 1 plus 1 plus 1. It's the next most complex circuit. Now, in order to build a full adder, you'll notice we need 2 AND gates, 2 XOR gates, and another OR gate. So, this means we're increasing the number of transistors here quite a bit. And it turns out that using transistors to double the processing power, we've got to at least double the number of components. And this leads, mathematically, this leads to what we call exponential growth. Okay, so we have an exponential growth in the number of transistors. And that's why in your mobile phone and in your computers, you have these little circuits, but on the circuits, there are billions of transistors. Okay, so to get the computers to perform, we need billions and billions of transistors. Now, if instead of using transistors, we use threshold oscillators. So here's our schematic of the half adder to add 2 bits together. To go from a half adder to a full adder with transistors, we don't even need any more threshold oscillators. We just need another input. And this gives us a full adder. And it turns out that with using threshold oscillators, we can double the processing power with a linear increase in components. Now, this is where the power of the brain comes in. So I'll try and explain this to you now. So the human brain is the most powerful computer known to the human race. And the average human brain consumes about 24 watts of power. Yet, so if you look at your light bulb, the light bulb will probably be burning more than your brain is at the moment. Now, IBM have estimated if they were to make a computer out of transistors, which could perform the tasks of one human brain, the computer would be huge. It would take up a massive building, and you would need a nuclear power station to power that transistor-based computer. So you'd need hundreds of megawatts of power to power that transistor-based computer. So transistor-based computers are very, very inefficient. Yeah? And our brains, which use, are very, very power efficient. Okay, now as well as performing logic, adding numbers together, multiplying numbers, introducing functions, all of that, we also need to perform memory. Okay, and there's a massive problem at the moment. So with these supercomputers, the computers are getting faster and faster, the logic's getting better and better, but scientists are having problems with memory. The memory is lagging behind the logic. So how do computers store memory? Well, the picture on the left here is what we call a set reset flip-flop. And a set reset flip-flop is used to store memory in computers. And again, you'll see there's a very simple schematic here of a breadboard with an integrated circuit here. You've got 2 switches. So this is your reset and this is your set. And then we have a Q and a not Q. Okay, so this is called a set reset flip-flop. And the way to think about this is, I've got the graph here. If not Q is on, then if you press R, it switches Q on and not Q. So if Q is on, so in this case, you can see Q is on. If you push this button here, it will cause a flip, and this LED would go on and this one would go off. So it's called a set reset flip-flop. Now, using transistors, we have to do something called line charging. You have to charge this whole line to cause a switch, which again, that costs power. Now, there's an added advantage again if we use threshold oscillators. So this is the circuitry for a threshold oscillator, and you can see how similar it is to the transistor circuitry. Yeah, we have some excitatory connections here, and the oscillators, the threshold oscillators, are mutually inhibiting one another. So oscillator 1 is trying to inhibit oscillator 2, and oscillator 2 is trying to inhibit oscillator 1. And this circuit does act like a set reset flip-flop. So not only can we perform logic using threshold oscillators, but we can also perform memory. Now, in 1962, Brian David Josephson predicted something called the Josephson effect. And this is now superconductors. So again, we're going back to physics. So Brian Josephson discovered that you have these superconducting materials, so a superconductor either side with an insulator in between. If you drop these devices down to 4 Kelvin, which is minus 269 degrees centigrade, I'll say that again to help you get your heads around it. 4 Kelvin is minus 269 degrees centigrade. If you get the temperature down to that level, then these devices become what we call superconductors. It means that current flows and we don't need any voltage. You don't consume any power. So we have current flows without any power. Now, these devices, these Josephson junctions, are a lot like the neurons in our brain. Okay, remember the neurons in our brain are natural threshold oscillators and they can oscillate 1,000 times in 1 second. Well, these devices, these Josephson junctions, can be built 1,000 times smaller than the neurons in your brain. And get this, they oscillate 100 million times faster than the neurons in the human brain. Now, I know that is impossible to get your head around. Yeah, so these devices become superconducting at minus 269 degrees centigrade, and they can oscillate 100 million times faster than the neurons in the brain. And they can be built 1,000 times smaller than the neurons in the brain. Okay, so this is the way to think about threshold oscillators. So again, using Python or Maple or Mathematica, we can solve the equations using maths packages. If we are below threshold, then your trajectory just goes to this point and there's no oscillation. Again, here we're below threshold, so we just go here and there's no oscillation. Now, the simple way to think about this is with a petrol lawnmower. I'm sure you've all seen petrol lawnmowers. There's a cord. If you give a yank on this cord and it's not hard enough, if you don't go above threshold, then it doesn't oscillate, it just stops. But if you give a hard enough yank on this cord, then we get it to oscillate. Yeah, and this is how we mow our lawns with these oscillating lawnmowers. And that's the way to think about these Josephson junctions or neurons in the brain. If you give enough kick to them, they will start to oscillate. So that's what we mean by threshold oscillator. Okay, now in 2010, University simulated circuits with Josephson junctions. So these big X's here represent Josephson junctions. These squiggly lines are called inductors. This parallel line is called a capacitor, and these wiggly lines here are called resistors. So you can see you got resistors, capacitors, inductors, and these Josephson junctions. So you can use electric circuitry, and you can get this part of the circuit to act exactly like a neuron. Yeah, this part of the circuit acts exactly like a neuron, and this part of the circuit acts like a synapse. If this bias current here is positive, then this neuron can switch another one on. So we've got excitation. So using using Josephson junctions, we can build electrical neurons, not biological. This is all electricity now. And if the bias current inhibit a neuron, so we've got excitation and inhibition with Josephson junctions. Okay, now this is just to show everybody there that, scientists, mathematicians, physicists, we're all just human beings. This is Ken Segal. He came to see me a few years ago, and we were playing table tennis in the back garden. Okay, a lot of children don't realize that a lot of scientists are also very good at sport, or we're very good at music. We have other pastimes. We don't just do science all day, every day. We're just normal human beings. Okay, so the picture on the left here is showing the blue excitatory neuron switches a green one on. So here's excitation. And the picture on the right is showing a blue neuron here is switching the green one off. So we've got excitation and inhibition. Now, as well as being theory, you see in 2017, so this is no longer theory, they actually built physical Josephson junction circuits where the neurons, Josephson junction neurons, synchronized and desynchronized in picoseconds. A picosecond is 100 100,000 million times faster, it's 100 million times faster than biological neurons. And more recently, if any of you have heard of MIT, MIT is the most famous university in the whole world. There's a group there who've now designed these artificial neurons using something called a superconducting nanowire. So as well as Josephson Junctions, you can also use superconducting nanowires to act like neurons as well. So there's lots of avenues of research still to come. In 1971, Leon Chua, so here's a picture of Leon Chua, who visited Manchester a few years back. John Borison is my co-inventor, and he was my student many years ago. This is me, this is Stephen Lynch, and Steve Ferber. I don't know if any of you have heard of the Spinnaker project in Manchester. So Steve Ferber is famous all around the world. And again, they're building a new type of computer based on brain dynamics in Manchester. Now, in 1971, Leon Chua was looking at how resistors relate current and voltage, inductors relate current and flux, capacitors relate voltage and charge, but he noticed there was a gap. There was nothing to relate charge and flux. So, in the future, some of you may do physics. Yeah. And anyway, a lot of you may have heard of inductors, resistors, and capacitors. Well, there is a new kid on the block. There is a new device called a memristor. And a memristor is acts like a resistor, but it has hysteresis. And so he invented that. Well, again, this is showing the mathematics. So in 1971, Leon Chua proved the existence of this device using mathematics. Okay, using mathematics. And in 2008, so 37 years later, HP Labs built a memristor. So again, hopefully that's showing you the power of mathematics. And if you connect a memristor to an oscilloscope, then you can see you get this, what we call pinched hysteresis. Now, memristors are important again for our invention because memristors act like synapses. Okay, so we're hoping we can use these memristors to connect our neurons together. Okay, now a few minutes ago, you'll remember I said that with our invention, we can double the processing power with a linear increase in components as opposed to an exponential increase in components. Now, this is a really nice picture because it's showing you the difference between exponential growth and linear growth. So if our invention works, the chip on the left here, this is the world's fastest arithmetic logic unit chip. And on this chip, there are 8,000 Josephson Junctions. 8,000 Josephson Junctions on this chip. On the right is a picture of the world's most powerful transistor-based supercomputer. Now look at the size of this thing. It takes up a whole building. And this billions of transistors. So this is the Japanese Fugaku supercomputer. And you can see it consumes 30 to 40 megawatts of power. You need a nuclear power station to operate this computer. And as I said in the abstract, it costs hundreds of thousands of pounds just to run this computer. Now, if our invention works, this one chip, would be more powerful than this transistor-based supercomputer. Okay, so in the future, we could have a laptop, and in that laptop, there'd be a small cryogenically cooled unit with one chip, and that computer could be more powerful than the world's fastest transistor-based supercomputer. Now, we can also talk about science fantasy here. What if in the future, we could build a computer this size using Josephson Junctions? And that's where it does get really scary. How intelligent would that computer be? Yeah, imagine a computer this size made up of Josephson Junction circuits. Okay, that's the first avenue of research. Second one, I'll just cover in 5 minutes, is to do with medicine and biology. So the human body can suffer from over 500 neurological conditions. So this is nothing to do with computing now. This is medicine and biology. So some of you may have heard of Alzheimer's disease, autism, Parkinson's disease, epilepsy, stroke and tetanus, brain damage, cerebral palsy, and the list goes on and on. Okay, what we are proposing is we want to connect biological neurons together. So these little lights here are biological neurons under a scanning electron microscope. The picture here is of a multi-electrode array, and these black lines here with the dots, these are called electrodes. So we can pass electricity through these electrodes, and we can switch neurons on and off. As well as doing that, these electrodes can also read the electrical current generated by the neurons. So this goes back up the wires. We can put this multi-electrode array on this device here, connect it to a computer. And here, believe it or not, this is not science fiction. On the computer here, you can see that there are some biological neurons oscillating. Okay, you can just about see the oscillations on the computer screen there. So believe it or not, there are neurons on this Petri dish which are oscillating, which are alive. So what we are proposing to do is we're going to make little logic circuits and little memory circuits out of biological neurons. And then we can check the functionality of those logic and memory circuits using drugs. Yeah, drug A, drug B, drug C, and hopefully this will help with research into Alzheimer's disease and Parkinson's disease, etc. So currently, the world does not have an assay where we can connect neurons together and get them to, act like a calculator. So that's what our invention will do. Okay, so we're working with Dr. Mark Cotter from Cambridge University, and we're also working with Dr. Paul Roach from Loughborough University. And as you can see, we published a paper in 2020 explaining mathematically how we are going to do this, but now we've got to do it biologically. We've got to do the wetware experiments. There's a research group at Harvard who've genetically modified a worm, and believe it or not, they can switch neurons on and off by shining light on the neurons. You can also use fluorescent dyes, so you can get excitatory neurons to glow green when they oscillate, and we can get excitatory neurons to glow red when they oscillate. So in the future, you may see our circuits on the TV, with people shining light on the neurons, and we'll have our half adders, full adders, and our set reset flip-flops, and we'll be checking the functionality of circuits for Alzheimer's disease, Parkinson's disease, etc. I do run national workshops for the IMA, so I know somebody was asking about R. I don't run R workshops, but I do run Python for A-level maths and beyond workshops. So if you look on the IMA website and conferences, you'll see that I run 4 of these every year. And if any of you do go to university in the future, one of you may, well, a few may do I do international workshops on Python for scientific computing and TensorFlow for artificial intelligence. So I've been invited all over the UK, and I've been invited to Malaysia, Singapore, China, and where else? The USA. Yeah. So I give this 5-day workshop. So I may, whichever university you end up with, I may come to your university and deliver this workshop. Okay. If you are interested in my research, you can go to ResearchGate, and you can download my papers for free. If you just type in ResearchGate Stephen Lynch, and you can download the papers for free. The neuron here on the right is a cuddly neuron, which you can buy from Amazon. I think they retail for about £7.99. So you can buy cuddly neurons. Okay, and I think we've got 5 minutes now for questions.
Yes, great. We've had one here. I think it's from a STEM enthusiast, which says, which degree involves as much maths, computer science and biology as possible?
Yeah, that's a very good question. And unfortunately, I don't think any university offers a degree where you do all of the STEM subjects. Having said that, I would say if you do a maths degree, mathematics is the best bet in order to study the other topics in parallel. So for example, you can do mathematical biology, you can do mathematical computing, you can do mathematical physics, you can do mathematical chemistry, but it doesn't really work the other way around. So yeah, so I'm a mathematician. I was actually trained as a pure mathematician. Yeah, but then I kind of became an applied mathematician, and now I'm doing lots of electrical engineering, lots of physics, lots of chemistry, lots of biology, lots of computing. So all of the STEM subjects.
Great. And which degrees did you actually take to get to your current role now?
Yeah, so I did my degree in pure mathematics, so very, very pure mathematics. But luckily, when I started my job, I shared a room with a physicist. So I, so that started me off really. So I was doing research with a physicist. Then I did some research with some material scientists. Then I did some research with some microbiologists. Then I did some work on muscle. Then I did some work with computer science. So it's I'm a lot older than I look. I'm like nearly 60, and it's taken me a long time to learn all of these disciplines.
And another question is, do you have any advice for students post-secondary school who might want to get into this industry?
Yeah, I think whichever industry you go into nowadays with modern technology, you've all got to learn to program. Programming is going to be so important in the future, and the best programming language to learn is called Python. So Python is now being taught in primary schools, and it's being taught in secondary schools, and it is going to be taught more and more at university level. But again, if you look at employability figures, Python is used extensively in industry. So I'd advise you to learn programming, whichever discipline you do.
Wonderful, thank you. I think that's all the questions that are on our Q&A and have come through on my emails. So I'd just like to take this opportunity to thank you so much, Stephen. Obviously, if any students have any questions which they haven't had a chance to pose on the Q&A, if they send it to me, are you happy for me to pass them on to you?
Yeah, of course.
Perfect, thank you so much.